somewhere on this planet, there is a place that should not be there. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. Picture the Earth from very high above. You see the slow curve of continents, the pale wash of deserts, the dark green press of forests, the silver threads of rivers finding their way to the sea. From that distance, the planet looks orderly. It looks like a place that follows rules, and mostly it does. Rocks form in ways we understand. Rivers carve valleys in ways we can predict. Mountains rise and fall according to forces we have studied for centuries. But then you come closer. You drop down through the clouds, and you find them. Places that do not fit. A circle of ancient rock in the middle of the Sahara Desert. So perfectly round it looks, as though something pressed a giant thumb into the sand millions of years ago. Stones the size of houses sitting in a field in Costa Rica. So smooth and so nearly perfect in their roundness that people still argue about how they got there. A forest in Poland where every single tree bends in the same strange direction, curving low to the ground and then rising again like a row of frozen waves. A crater in the middle of a desert in Turkmenistan that has been on fire for decades, burning quietly in the dark, and no one is entirely sure what to do about it. These places exist. You can visit them. You can stand in them and look around. And yet, for all of our science, for all of our tools and satellites and soil samples and computer models, many of them remain genuinely, honestly unexplained. That is what this long, quiet night is about. Not the kind of mystery that lives in old stories or ancient legends, though those are worth their own evenings. This is something different. This is the mystery that lives inside peer-reviewed papers and geology conferences. Inside the careful notes of researchers who have spent years trying to understand a single hill, a single lake, a single field of stones. The mystery that says, we have good theories, but we are not sure. The mystery that says, the evidence points in two directions at once, and we have not yet found the thing that settles it. There is something deeply comforting about that, if you sit with it long enough. The earth is old, older than almost anything we can hold in our minds. 4.5 billion years old, give or take. In that time, it has been through events we can barely imagine. Continents have drifted and crashed into each other. Oceans have appeared and disappeared. Ice has covered the whole planet and then retreated. Volcanoes have reshaped entire regions. Life has risen and in some cases nearly vanished and then risen again. All of that history is written in the rock and the soil and the water, but it is not always written clearly. Sometimes the record is smudged. Sometimes the forces that shaped a place were so unusual, so specific to a single moment in time, that we have no good comparison to measure them against. And sometimes, honestly, we just do not know yet. That is not a failure of science. It is science working exactly as it should, sitting with a question, turning it over, offering a careful guess, and then checking that guess against the evidence, and sometimes finding that the evidence says, not quite. Tonight, we are going to visit some of those places together. We will stand at the edge of things that puzzle the people who study them most. We will look at the theories, and we will look at the places where the theories fall short. We will not rush. There is no urgency here. These places have been waiting for answers for thousands, sometimes millions of years. They can wait a little longer, and as you listen, as your body settles and your breathing slows, maybe the questions themselves become something pleasant to carry. A soft weight, a small, gentle wonder to hold as you drift. The earth is full of places that should not exist, and the fact that they do exist quietly and patiently out there in the dark right now is one of the strangest and most beautiful things about the world we live on. Let's begin. Beneath your feet right now, the ground is not still. It may feel solid. It may feel permanent. But the earth beneath us is always doing something. It shifts, it settles, it swells, and in certain places, it does something that looks almost like breathing. The surface rises and falls. Slowly, yes. Quietly, yes. But it moves. This is not a figure of speech. In some parts of the world, the ground actually pushes upward from below, forming rounded mounds that grow over years and decades. These mounds are called pingos. A pingo is a hill made mostly of ice, covered in a thin layer of soil and grass. From a distance, a pingo looks like a gentle dome rising out of flat land. Up close, it can be enormous. Some pingos grow to 30 meters tall. That is roughly the height of a 10-story building, rising out of what was once flat ground, pushed up entirely by the pressure of freezing water underground. They are found mostly in the Arctic, in places like northern Canada, Alaska, Siberia, and Greenland. The land there is called permafrost, which means the soil beneath the surface stays frozen all year round. When water gets trapped inside that frozen ground and then freezes itself, it expands. Ice always expands when it freezes. And when there is nowhere for that expansion to go, it pushes upward. The ground above it has no choice but to rise. A pingo can take hundreds of years to reach its full height. Some are thought to be thousands of years old. They grow so slowly that no single person would notice the change from one year to the next. But over a long human lifetime, the difference can be measured. The ground breathes on a timescale we are not built to feel. What makes pingos strange is not just that they exist. It is that they sometimes collapse. When the ice core inside melts, the hill sinks. It falls inward on itself, leaving behind a ring-shaped depression in the ground, like a crater with soft edges. From above, these collapsed pingos look like circles pressed into the earth. Some researchers have looked at ancient circular marks in landscapes far outside the Arctic and wondered if those, too, might be the ghosts of old pingos from a colder time. That question is genuinely open. The evidence is incomplete. Some circular features in temperate regions, places that are no longer frozen, do seem to match the shape of a collapsed pingo. But other researchers argue those same shapes could come from entirely different causes. Old sinkholes, ancient lake beds, or even meteor impacts at a very small scale. The ground keeps its secrets well. Pingos have a smaller cousin called a palsa. A palsa is similar in structure, but shorter and less dramatic. Palsas tend to form in boggy, wet ground, and they rarely grow taller than a few meters. They are common across Scandinavia and parts of northern Russia. Like pingos, they are made of frozen ground pushing upward. And like pingos, they can collapse when the climate around them warms. This is where the science becomes urgent in a quiet way. Both pingos and palsas are sensitive to temperature. As the climate changes, some of these frozen mounds are melting faster than they once did. Researchers who study them have noted that certain palsas in Scandinavia have shrunk measurably over the past few decades. What was once a gently breathing landscape is exhaling for what may be the last time in a very long while. But here is what remains unresolved. We do not fully understand all the conditions that cause a pingo to form in one place and not another. Two patches of permafrost can look nearly identical, and yet one will produce a pingo and the other will stay flat. The internal plumbing of the frozen ground, the way water moves and pools and freezes beneath the surface, is still being mapped. The models researchers use to predict where pingos will grow are good, but not perfect. There is also the question of what happens to the land after a pingo collapses. The crater it leaves behind can fill with water, becoming a small pond. That pond changes the local ecosystem. Plants grow differently around it. Animals use it. The collapse of one frozen mound can quietly reshape a whole small corner of the world. The ground breathes. It rises over centuries and falls again. It leaves marks that outlast the ice that made them. And in those marks, in those soft circles pressed into the earth, there are questions that researchers are still working to answer. The earth is patient. It has been doing this long before anyone was watching. There are places on Earth where a compass needle does not point north. It spins. It drifts. It settles on a direction that has nothing to do with the magnetic pole far above the Arctic Circle. Sailors have noticed this for centuries. Pilots have logged it in their records, and geologists, even now, do not have a single clean answer for why certain patches of ground seem to pull at the invisible lines of Earth's magnetic field and bend them out of shape. To understand why this happens, it helps to go back a very long way, back to when the ground beneath your feet was not yet ground at all. The Earth formed roughly 4.5 billion years ago from a spinning cloud of dust and gas. As it grew, the heaviest materials sank toward the center. Iron and nickel fell inward slowly over millions of years and pooled into what we now call the core. The outer part of that core is still liquid today. It moves, it churns, and that churning, spinning metal is what generates Earth's magnetic field, the invisible force that wraps around the planet like a shell you cannot see or touch. That field is not perfectly smooth. It has wrinkles. It has patches where it pulls stronger and patches where it seems to fade. Some of those patches sit right at the surface, locked inside certain kinds of rock. The rock responsible is often called magnetite. It is a dark, heavy mineral with iron woven through it. When magnetite forms inside cooling lava, something remarkable happens. The iron atoms inside the mineral line up with whatever direction Earth's magnetic field is pointing at that moment. They freeze in place as the rock hardens. The rock becomes, in a sense, a record of the magnetic field from the day it was born. This is part of how geologists read the history of the planet. They look at old lava flows and measure which direction the magnetite is pointing. But here is where things get strange. In some places, the magnetite is so dense, so concentrated, that it creates its own local magnetic field. A field strong enough to confuse a compass, strong enough to make the needle swing away from north and point at the ground beneath your feet instead. One of the most studied examples sits in a region of northern Canada, near a body of water called Magnetic Hill. Another appears in parts of the Kursk region in Russia, where iron ore deposits so vast and so close to the surface that they distort the local field for hundreds of kilometers in every direction. Pilots flying over certain parts of that region have reported instruments behaving in ways that took careful calibration to correct. But the origin story does not end with magnetite. Some researchers believe that ancient meteor impacts also play a role. When a large rock from space strikes the Earth, the heat and pressure of the impact can melt the ground and create new minerals. Some of those minerals are magnetic. The Sudbury Basin in Ontario, Canada, is one place where scientists have found unusual magnetic readings tied to what appears to be a very old impact site. The crater is so ancient it has been worn almost flat by time. You would not know it was there just by looking. But the magnetic signature remains. There is a competing idea, though. Some geologists argue that the magnetic strangeness in certain places has less to do with the surface rock and more to do with deep structures far below. The crust, the thin outer shell of the planet, sits on top of the mantle, that thick layer of hot rock between the crust and the core, where the crust is thin, or where ancient fault lines have shifted rock into unusual positions. The magnetic field can leak through in unexpected ways. The surface might look perfectly ordinary, but deep below, something is different. What makes this hard to resolve is that we cannot see down there. We can drill a few kilometers. We can send sound waves into the ground and listen to how they bounce back. But the deep structure of the earth remains, in many places, a matter of careful inference rather than direct observation. So when a compass needle drifts in a quiet valley or spins slowly above a stretch of dark volcanic rock, the honest answer is that we are reading a signal from very deep in time. The rock remembers something. The field is responding to forces that were set in motion long before anything walked on this planet. We can measure the effect. We can map it. We can offer several good explanations for how it might have formed. But the full story in many of these places is still being written. There are lakes on this planet that should not be able to hold life, not by any ordinary measure. The water is too salty, too hot, too acidic, or too thick with chemicals that would dissolve most living things in minutes. And yet, when scientists lower instruments into these places, they find life. Quiet, patient, strange life, clinging to the rocks, drifting in the water, breathing in ways that nothing should be able to breathe. This is one of the quieter mysteries Earth keeps. Consider the lakes that sit inside volcanic craters. Some of them are so acidic that the water approaches the strength of battery acid. The color is often a pale, milky green, or a deep sulfurous yellow. The smell, if you stood at the edge, would be sharp and chemical. Most organisms cannot survive in water like that. The proteins that hold living cells together simply fall apart, and yet certain microbes, tiny single-celled organisms far too small to see have been found living in these waters. How they manage this is still an open question. One idea is that they have developed a kind of chemical armor, a way of keeping their insides stable even when the outside world is hostile. Another idea is that they have been living in these conditions for so long that they have slowly changed, generation by generation, into something that no longer needs the conditions the rest of life depends on. Neither explanation is complete. The full picture is still being worked out. Then there are the salt lakes, places like the Dead Sea, where the water holds so much dissolved salt that most fish cannot survive in it. The salt concentration is roughly 10 times higher than ordinary ocean water. Objects float in it easily. The density of the water is simply too high for most aquatic life to function. And for a long time, people assumed these lakes were dead in the truest sense. Empty, barren, but they are not. Certain salt-loving microbes thrive in them. Some of these organisms turn the water pink or red, coloring entire lakes in shades that look almost painted. The pigment they produce helps them absorb light in a way that protects them from the intense brightness that reflects off the salt. It is a solution so elegant that researchers are still studying exactly how it works at the chemical level. The minerals in these lakes are ancient. Some of the salts and compounds dissolved in extreme lake water have been accumulating for thousands or even millions of years. They arrived through rain, through rivers, through the slow dissolving of surrounding rock. Some of the iron compounds found in certain volcanic lakes were forged inside dying stars long before the Earth existed. The iron traveled through space, settled into the young planet, and was eventually carried by water into these strange, quiet basins. It is a long chain of events, stretching back further than the mind can easily hold. Some lakes are strange for a different reason entirely. There are meromictic lakes, lakes where the deep water and the surface water never mix. In most lakes, wind and seasonal temperature changes stir the water from top to bottom, keeping it relatively uniform. But in meromictic lakes, the deep water is so dense, often because of dissolved minerals or gases, that it simply stays put. The bottom layer can be thousands of years old. It holds gases, compounds, and sometimes ancient organic material that has been sealed away from the surface world for longer than recorded human history. Researchers have pulled samples from these deep layers and found chemistry that does not match anything in the upper water. Some of those samples contain gases produced by microbial life that has been isolated down there in the dark for an extraordinary length of time. What that life has become, cut off from the surface, is genuinely unknown. One theory holds that isolated deep lake ecosystems may have evolved along entirely separate lines from surface life, developing chemical processes that have no equivalent anywhere else on Earth. Another view is more cautious, suggesting that the differences are real but modest, and that the same basic chemistry underlies all of it. The debate is ongoing. The samples are difficult to collect without contaminating them. The analysis takes years, and so these lakes sit quietly in their craters and their valleys and their salt flats. They hold their chemistry close. They sustain life that should not be there, in water that should not allow it, using minerals that arrived from the far edges of deep time. The question of how they do it, and what exactly lives in the deepest, oldest layers, remains open. The water keeps its answer just below the surface, still and patient, waiting for instruments and ideas that do not yet exist. There are forests in the world that make a sound no one can fully explain. Not the creak of branches in wind, not the rustle of leaves in a breeze. Something deeper, something that seems to come from the ground itself, rising up through the roots, through the soil, into the air around you. A low, steady hum, felt as much as heard. The crooked forest in western Poland is one of the quieter mysteries on Earth. It sits near a small town, surrounded by ordinary pine trees, standing straight and tall. But inside this grove, roughly 400 trees grow in a way that should not be possible. Each one bends sharply at the base, curving northward in a smooth arc before turning upward again. The curve is almost identical from tree to tree. The bend is gentle, not broken. The trees are alive and healthy. No one knows why. is not an exaggeration. Foresters, botanists, and geologists have studied the grove for decades. Several theories exist. None of them fully satisfies. One idea is that the trees were shaped by human hands. Sometime in the 1930s, before the grove was abandoned during the Second World War, farmers may have bent the saplings on purpose. Curved wood was useful. It could be shaped into the hulls of boats, into furniture, into the runners of sleds. If you bend a young tree and hold it in place long enough, it will grow that way. The shape becomes permanent. This explanation has a certain logic. The trees are all roughly the same age, which suggests they were planted at the same time. The curve is consistent, which suggests something deliberate. But the theory has gaps. No written record confirms it. No tool marks survive. No one who worked those fields left behind a clear account of what they were doing, or why the project was abandoned. A second theory points to the ground itself. Some researchers wonder whether a heavy snowfall or an ice storm struck the saplings when they were very young, pressing them flat against the earth for a season or more. When the weight lifted, the trees grew upward again, but the bend had already set into the wood. This happens in nature. Trees recover from damage in remarkable ways, and the memory of that damage stays in the grain of the wood forever. But this theory also has problems. A natural event like a snowfall would not bend every tree in exactly the same direction with exactly the same curve. The uniformity is what makes the grove strange. Nature tends toward variation. This grove tends toward repetition. And then there is the hum. Several visitors to the Crooked Forest have reported a low vibration in the air, a feeling of pressure or resonance that is difficult to describe. Some say it is the wind moving through the curved trunks in an unusual way. The shape of the trees creating a kind of natural instrument. The bend, they suggest, catches air differently than a straight trunk would. The sound is just physics, just air moving through an unusual shape. Others are less certain. Some researchers who study forest acoustics, the science of how sound moves through trees and soil, have noted that forests can act as amplifiers for very low-frequency vibrations in the earth. These vibrations called infrasound, sit below the range of normal hearing. You cannot hear them as a tone, but your body can feel them. Some studies suggest that infrasound can produce a mild sense of unease, a feeling that something is present without being visible. Whether the crooked forest produces infrasound is not confirmed. Whether the hum visitors report is real or imagined is an open question. The human mind is very good at finding patterns and sensations in places it has been told are strange. But the trees themselves are not imagined. They are there. They bend. They curve. They stand in rows that feel almost deliberate, almost designed, almost like a message written in wood that no one has yet learned to read. The forces that shape a living tree are not simple. Gravity pulls it down. Light pulls it upward. Water moves through it under pressure. The soil pushes back against its roots. Wind bends it one way, then another. Over years, over decades, the tree negotiates all of these forces at once, and the shape it takes is the record of that negotiation. In the crooked forest, something interrupted that negotiation early. Something pushed or bent or pressed, and the trees remembered. What that something was, the forest has not said. The hum continues, low and steady, just below the edge of understanding. The curved trunks stand in their quiet rows. The question of what shaped them remains, for now, open. Somewhere in the desert of Death Valley, California, there are rocks that move. Not quickly, not visibly, but they move. A stone the size of a small television set sits on a flat, cracked lake bed, and behind it stretches a long, shallow groove in the mud, a trail, sometimes straight, sometimes curving gently, sometimes turning almost back on itself. The rock has been somewhere else. Something carried it, or pushed it, or slid it across the ground. And for a long time, no one could say what. The lake bed is called racetrack playa. Playa is a word for a flat, dry basin that fills with shallow water after rain, then bakes hard in the sun. The surface of racetrack playa is cracked into small polygons, like the skin of something ancient. It is almost perfectly level, and scattered across it are these stones, some weighing just a few pounds, some weighing as much as 300 pounds, roughly the weight of a large refrigerator, each one sitting quietly at the end of its own mysterious trail. The trails themselves are worth thinking about slowly. Some run for 30 feet. Some run for nearly 1,000 feet. That is longer than 3 American football fields laid end to end. A rock the weight of a refrigerator, moving nearly 1,000 feet across open desert, leaving a clean groove behind it. No footprints around it. No wheel marks. No sign of any machine or animal, just the stone and the line it drew. For decades, the most popular theory was wind. Death Valley produces fierce, sudden windstorms. Some researchers thought that when the playa flooded after rain and then froze into a thin sheet of ice, the wind could push rocks across the slick surface. The ice would lower friction, the resistance that normally holds things in place, and a strong gust might be enough to send even a heavy stone sliding. It was a reasonable idea, but it was hard to test because no one had ever actually watched a rock move. Then, in the early 2010s, a small group of researchers set up cameras and sensors around the playa and waited. They waited through seasons. They came back repeatedly, and eventually they caught it. The rocks moved during a very specific set of conditions. A thin layer of ice formed on the flooded playa overnight. And then, as the morning sun warmed the air, the ice began to break apart into large floating panels. Light winds, not fierce storms, but gentle breezes, pushed those ice panels across the water. The panels nudged the rocks. The rocks slid. Slowly, quietly, almost imperceptibly, they moved. It sounds like a solved mystery, but many researchers say it is only partly solved. The cameras captured some rocks moving. They did not capture all of them. Some of the trails on Racetrack Playa are far older than any recent observation. Some trails show patterns, sharp turns, parallel lines, rocks that seem to have moved in groups, that the ice panel explanation does not fully account for. One competing idea is that different rocks move by different mechanisms, and that the playa has more than one process at work across its long history. Another is that some trails were made under conditions that no longer occur. Perhaps during wetter periods thousands of years ago, when the playa held deeper water for longer stretches of time. The scale of the mystery is part of what makes it linger. A 300-pound rock moving nearly 1,000 feet is not a small thing. If you tried to push that rock yourself across a flat, dry surface, you would need real effort. You would feel the weight of it, and yet something gentle enough to leave no other mark on the landscape accomplished that same task quietly in the dark or in the early morning while no one was watching. There is something almost meditative about the image. A vast, silent, cracked lakebed. The pale mountains ringing it on all sides. The sky enormous overhead. And in the stillness, a rock patient, heavy, indifferent, drawing a slow line through the mud as if it had somewhere to be. The question of exactly how, and exactly when, and exactly why some trails look the way they do is still being studied. The basic mechanism may be understood in broad strokes, but the full story of every trail on that playa, every turn and curve and doubling back, is not yet written. The rocks have been moving for longer than anyone has been watching, and the desert keeps its own record in lines of dried mud of everything it has seen. Imagine standing at the edge of a wide, shallow valley. The ground beneath your feet is pale and dry. The rock is old, very old. And yet, something about this place feels wrong in a quiet, hard-to-name way. The shapes are too regular. The lines are too clean. The land looks as though something arranged it long before any human hand could have done so. There are valleys on this earth that geologists return to again and again, not because they have found the answer, but because the answer keeps slipping just out of reach. One such place sits in the Sahara Desert, in what is now Mauritania. From the ground, it looks like a series of low, curved ridges rising from a flat, sandy plain. The rock is pale cream and dusty orange, worn smooth by wind and time. The ridges curve outward in wide arcs, one inside the other, like rings on the surface of still water after a stone has been dropped. From above, the whole structure is nearly 50 kilometers across. That is roughly the width of a large city, drawn in stone on the face of the desert. This is the Richat structure, sometimes called the Eye of the Sahara. And the question of how it formed is still, in many ways, open. The most widely held theory among geologists is that the structure formed through a process called erosion, the slow wearing away of rock by wind and water over millions of years. According to this view, a dome of rock once pushed upward here, and then the softer layers at its center wore away faster than the harder outer rings, leaving behind the circular pattern we see today. The rings are real geological layers, each one a different age and composition. Some contain ancient volcanic rock. Some contain sedimentary stone laid down in shallow seas that no longer exist. But not everyone is fully satisfied with that explanation. Some researchers point to the unusual symmetry of the rings and wonder whether an impact from space might have played a role. A meteorite strike can leave circular patterns in rock, and the Richat structure is round enough to raise the question. However, most geologists who have studied the site closely say the evidence does not support an impact origin. The rock types present are not what you would typically find at an impact crater. The question of exactly how the dome formed in the first place, what pushed it upward, is still being studied. What makes the Richat structure feel so strange when you stand near it is the texture of the land itself. The rock is fractured and layered, stripped bare by the desert wind. There are no trees. There is almost no soil. The surface is all stone and shadow, pale ridges, casting long lines across the sand in the early morning light. The colors shift as the sun moves cream to gold to deep amber. It is enormous and silent and very, very old. And it is not the only valley that resists easy explanation. In other parts of the world, there are valleys where the surface tells a story that the surrounding land does not seem to support. Flat-bottomed valleys in regions where the rivers that should have carved them are long gone. Wide, smooth depressions in landscapes that show no obvious sign of the force that shaped them. Geologists call some of these features relict landforms, shapes left over from conditions that no longer exist, carved by glaciers or ancient floods or climates so different from today that they are difficult to fully reconstruct. One theory holds that many of these valleys were carved during periods of intense glacial melt, when enormous volumes of water moved across the land in ways that are hard to model precisely. Another theory suggests that some flat-floored valleys formed not through erosion from above, but through the slow collapse of material underground, caves dissolving, rock settling, the surface sinking gently over thousands of years. Both ideas have evidence behind them. Neither fully explains every case. What stays with you thinking about these places is the sheer patience of the process. The land does not hurry. It shifts and wears and settles across timescales that make a human life feel like a single breath. The valleys we cannot explain are not strange because something dramatic happened. They are strange because something slow and vast and quiet happened, and we are still piecing together what it was. The pale ridges of the Richat catch the last light of afternoon. The empty valley floor stretches out in all directions. The wind moves across the stone without a sound. Whatever shaped this place did so long before anyone was here to watch. And the land, as always, keeps its own counsel. Beneath the surface of the earth, strange things happen. Things that instruments can measure, but cannot fully explain. One of the strangest is light, not sunlight filtering through water, not the glow of a lantern or a fire. Light that appears in places where no light should be, rising from the ground itself, drifting through the air above certain landscapes, soft and pale, and without any clear source. These lights have been reported for centuries. People living near certain hills, certain bogs, certain coastlines have described them in quiet, careful language. A pale glow above the marsh, a flickering above the ridge, a soft blue shimmer moving slowly across the water. The reports come from so many different places, across so many different cultures, that researchers have had to take them seriously. Something is happening. The question is what? One of the most studied examples comes from a region in Norway called Hestalen. There, in a long, narrow valley surrounded by low mountains, lights have been observed regularly since at least the early 1980s. They float, they pulse, they change color from white to yellow to red. They move slowly, then stop, move again. Some last only seconds. Others linger for more than an hour. Scientists have set up instruments in the valley to try to record and measure them. The lights show up on radar. They emit radio waves. They are real physical phenomena. But what they are exactly is still an open question. One theory is that the lights are a form of plasma. Plasma is a kind of energized gas, the same basic stuff as lightning that can glow on its own. Some researchers think that the specific mix of minerals in the rocks beneath Hesdalen might create electrical charges as they grind against each other deep underground. Those charges could rise toward the surface and ignite the air into brief, glowing clouds of plasma. The valley sits along a geological fault line, a crack in the Earth's crust where two sections of rock press against each other, which might help explain why the energy builds up there in particular, but not everyone agrees. Other researchers point out that plasma behaves in predictable ways, and the Hesdalen lights don't always follow those patterns. Some of the lights seem to move with a kind of slow deliberateness that plasma clouds don't usually show. A competing idea suggests the lights might be related to ionized gas, meaning gas whose atoms have been electrically charged, rising from underground chemical reactions between sulfur-rich rocks and water. The valley has both. The chemistry could, in theory, produce glowing gas. But producing that gas in open air, in the quantities needed to make a visible light, is something researchers have not yet been able to replicate in a lab. There's a third possibility that some scientists find interesting, though it remains very much a hypothesis. Certain rocks, when put under pressure, can produce electrical charges on their surfaces. This is called the piezoelectric effect, and it's a well-documented property of quartz-bearing rock. The idea is that deep tectonic stress, the slow, constant squeezing of rock layers against each other, might generate enough surface electricity to ionize the air above the ground. The result could be a faint, drifting glow. Some researchers have tried to connect this idea to earthquake lights, which are brief flashes, sometimes reported before or during seismic events. The connection is suggestive, but it has not been confirmed. What makes Hesdalen unusual is that it has been studied so carefully and still resists a clean answer. Most strange lights reported around the world don't get that level of attention. There are similar reports from marshlands in England, from the bayous of the American South, from river valleys in South America. The old name for marsh lights is ignis fatuus, a Latin phrase meaning foolish fire. For a long time, the scientific explanation was simple. Decaying organic matter in wet ground releases methane and other gases, and those gases can sometimes ignite spontaneously, producing a brief, pale flame. That explanation covers some cases, but it doesn't cover all of them. Some reported lights appear in dry landscapes, far from any marsh or bog. Some appear at altitude, above rocky ridges, where there is no organic matter to decay. The Earth's crust is full of minerals, pressures, chemical reactions, and electrical gradients that we are still learning to read. The deeper you go, the less we understand. And some of what happens deep down finds its way to the surface in forms we don't yet have good names for. A soft glow above a valley at night, a shimmer that moves and then fades. The instruments record it. The theories multiply, and the light, quiet and unhurried, continues to appear. The ocean has its own kind of breathing. It rises and falls with the tides. It churns in great slow circles called gyres, vast loops of moving water that take years to complete a single turn. Most of the time, the sea follows patterns we can measure and predict. But there are places where the ocean seems to forget the rules. Places where the water does something that even careful, experienced researchers find difficult to explain. One of the strangest of these places sits in the waters between Norway and Denmark, in a part of the North Atlantic that sailors have crossed for centuries. Here, a current of warm, salty water from the south meets a wall of cold, dense water from the Arctic. The two bodies of water sit side by side without mixing. They have different temperatures, different salt levels, different colors, even one a deeper blue, the other a greener gray. The line between them is sometimes sharp enough to see from a boat. Scientists call this a halocline, a boundary where water of different salt content refuses to blend. is understood. What is less understood is why, in certain locations, this boundary holds so firmly for so long, and why in other places it breaks down without warning. The ocean draws its own borders, and it does not always explain why. Further south, in the waters off the coast of West Africa, there is a place where the sea surface sometimes glows at night, not from a ship's lights, not from the moon. The glow comes from within the water itself, a soft blue-white shimmer that rolls with the waves. This is bioluminescence, light made by living things, tiny organisms that flash when the water moves around them. It has been seen for centuries. Ancient sailors wrote about it. Some thought the sea was on fire. Others believed it was a sign of something below the surface, something large and restless. We know now that the light comes from microscopic creatures, but why certain patches of ocean glow so brightly, and why the same waters go dark for years before glowing again, is still not fully worked out. The cycles of bioluminescent blooms are tied to temperature, nutrients, and currents, but the exact triggers remain an open question. Then there is the matter of the Milky Sea. This is different from ordinary bioluminescence. The Milky Sea is a rare phenomenon where hundreds of square kilometers of ocean surface glow with a steady, pale, blue-white light for hours or even days at a time. It does not flicker. It does not pulse. It simply glows like a vast sheet of cold light spread across the dark water. Sailors have reported it for hundreds of years, and for a long time, many scientists thought it was exaggerated. Then, in the early 2000s, researchers found satellite images that appeared to confirm it. The leading theory is that it is caused by enormous concentrations of bioluminescent bacteria, not the flashing kind, but a type that glows continuously. But no research vessel has ever sailed into a confirmed Milky Sea event and collected enough samples to fully test that theory. The question of what exactly causes it and why it appears so rarely remains genuinely open. The ocean also has its own long, slow cycles that operate over thousands of years. One of these is the deep ocean conveyor, a system of currents that carries cold water down from the poles and warm water up from the tropics, moving heat around the planet like a slow engine. This system has paused before or slowed dramatically during past ice ages. Some researchers believe it is slowing again, though others dispute the evidence. What would happen to the places where the ocean already behaves strangely if that great conveyor changed its rhythm? Nobody knows for certain. There are also places in the ocean where the seafloor itself seems to breathe. Methane, a gas, seeps up through cracks in the rock and rises in slow columns through the cold water. These seep sites support strange communities of creatures that live without sunlight, feeding on the chemical energy of the gas itself. The seeps appear and disappear over decades. New ones open. Old ones go quiet. What drives that rhythm is still being studied. Some researchers think the seeps pulse in time with shifts in pressure from the water above. Others think the rhythm is deeper, tied to movements in the rock far below. The ocean is old. It has been cycling through these patterns for millions of years. And yet, in so many of its stranger corners, the full shape of those cycles is still coming into focus. The sea keeps its own time. We are still learning how to read it. Some of the strangest places on Earth are not wide open spaces. They are not vast deserts or rolling plains. They are narrow, dark, and hidden just below the surface of the ground we walk on every day. Caves sit beside us, beneath us, all around us. And some of them do things that no one has fully explained. There are caves on every continent. Most are quiet. Most are simply stone and water and time. But a few of them seem to behave differently from the rock around them. They carry sounds that should not be there. They hold air that moves when nothing outside is moving. They sit beside rivers, beside forests, beside ancient ruins, and somehow they seem connected to all of it in ways that are still being worked out. One of the most curious things about certain cave systems is the sound. Not the drip of water, not the echo of footsteps. Something else. A low, soft tone that visitors sometimes describe as a hum or a whisper. It rises and falls. It seems to come from everywhere and nowhere at once. Some researchers think the shape of a cave can act like a musical instrument. The stone walls, the curved ceilings, the narrow passages. All of it can catch moving air and produce a tone the way a bottle does when you blow across its opening. That is one idea. But another idea is more interesting and harder to test. Some caves sit directly above or beside underground water systems. The water moves through cracks in the rock far below. As it moves, it pushes air. That air travels upward through tiny passages and emerges as a breath, a sigh, a whisper from the stone. The cave is not making the sound on its own. It is connected to something deeper, something flowing, something the visitor cannot see. The cave is a neighbor to a whole hidden world below it. This is what the phase of this episode calls the neighbors. Nothing on earth exists alone. Every strange place sits beside something else. Every unexplained feature has a context, a surrounding system, a set of relationships that may be part of the explanation. Caves near coastlines sometimes breathe with the tide. The ocean pushes water into underground channels. The water compresses the air inside the cave. The cave exhales. Then the tide pulls back, and the cave inhales again. People standing at the entrance feel a wind that comes and goes on a rhythm. It can feel uncanny. It can feel alive. But it is the ocean, miles away, pressing gently through the rock. The cave and the sea are neighbors. They share a breath. Some caves in limestone regions sit beside ancient sinkholes and collapsed chambers. The ground around them is riddled with passages too small to enter, but large enough to carry air and sound. When researchers try to map these systems, they often find that the cave they can see is only a small part of a much larger network they cannot reach. The whisper might be coming from a chamber no one has entered. It might be coming from a space that has been sealed for thousands of years. The question of what is connected to what remains genuinely open in many of these places. There are also caves that sit beside sites of very old human activity. Painted caves in southern Europe, carved caves in the Middle East, ceremonial caves in Central America. In many of these places, the acoustics are remarkable. The spots where ancient people painted the walls are often the spots where the sound is richest, where a voice carries the farthest, where a hum resonates most deeply. Some researchers wonder whether the people who used these caves chose those spots partly because of the sound. Whether the whisper of the cave was part of the reason they came there at all. That idea is not proven. It may never be, but it raises a quiet question about how our ancestors understood the places around them. They lived close to the ground. They listened to it. They may have heard things we have stopped paying attention to. The cave does not exist alone. It exists beside the water table, beside the tide, beside the forest above it, beside whatever came before us and left its marks on the walls. All of those neighbors shape what the cave does, what it sounds like, what it feels like to stand inside it in the dark and hear something you cannot quite name. We have mapped many caves. We have measured their air and their water and their stone. But the full picture of how a cave connects to everything around it is still being drawn. The whisper, for now, is still a question. There are places on this earth where the ground simply opens, not slowly, not gently. One day there is solid land, the next a hole, and sometimes no one can say how deep it goes. These are not ordinary sinkholes. Ordinary sinkholes have explanations. Water dissolves limestone over many years. The ceiling of an underground space grows thin, and eventually the surface collapses. That process is well understood, but some of the deepest, strangest holes on Earth resist that tidy explanation. They are wider than they should be. They are older than the surrounding rock suggests. Or they simply keep going, far past the point where geologists expected to find solid ground. The Darvaza crater in Turkmenistan is one of the most striking holes on Earth. It sits in the middle of a flat desert, roughly 70 meters wide and about 30 meters deep. It has been burning continuously since the early 1970s, when a Soviet drilling operation is believed to have broken into an underground gas pocket. The ground collapsed, and the fire was lit, reportedly to burn off the gas before it spread. The fire has not gone out since. Decades of flame, fed by methane rising from deep below the desert floor. Locals call it the door to hell, though that name belongs to the imagination rather than to geology. What no one has fully resolved is just how large the gas reservoir beneath it truly is. Some estimates suggest it could burn for many more decades. Others wonder if the supply is far greater than early surveys indicated. The honest answer is that the full depth of what feeds that fire remains uncertain. Then there are the blue holes. These are circular, almost perfectly round openings in the ocean floor or in shallow coastal waters. The most famous sits off the coast of Belize. It drops nearly 300 meters straight down. The walls are vertical. The water at the bottom is almost completely still, with very little oxygen, which means almost nothing lives there. What makes blue holes strange is their shape. They are too round, too clean, too deep for the surrounding seafloor. The leading theory is that they formed during ice ages, when sea levels were much lower and the area was dry land. Rainwater, slightly acidic, dissolved the limestone over thousands of years, carving a cave. When the ice melted and the sea rose, the cave flooded and the ceiling collapsed. That would explain the shape. But some blue holes are so deep and their walls so perfectly smooth that researchers are still debating whether that process alone is sufficient. A few scientists have suggested that ancient geological faulting, where sections of the crust shift and crack, may have helped form them. The question of which force did more work is still open. There are also the giant karst sinkholes of southern China. These are called Tiankang, which means heavenly pit in Chinese. Some are over 500 meters wide and more than 400 meters deep. They are so large that entire ecosystems exist inside them, cut off from the world above. Ancient trees grow at the bottom. Species of plants and insects have been found there that exist nowhere else. The standard explanation is the same dissolving limestone process, but on a much grander scale, over a much longer time. What puzzles researchers is the speed at which some of these pits appear to have formed. The rock record inside some Tiankang suggests the collapse happened relatively quickly in geological terms, not over millions of years, but over thousands. Why some limestone regions produce these enormous pits, while others, with seemingly similar rock, produce nothing like them, is still being studied. And then there are are the holes that have no clear origin at all. In 2014, large craters appeared in the Yamal Peninsula in Siberia. They were tens of meters wide, with steep walls and no obvious debris around the rim. One theory holds that warming permafrost, the permanently frozen ground beneath the surface, releases trapped methane gas under pressure until the ground simply explodes outward. That idea has some support, but the exact mechanism, the pressure required, the depth of the gas pockets, the trigger that causes one spot to blow while another does not, remains genuinely unclear. A competing theory suggests that underground ice melts and collapses, leaving a void that the surface then falls into. Both explanations have evidence behind them. Neither has been confirmed as the full answer. What all these places share is a kind of vertical mystery. The earth opens, and the opening goes far deeper than expected. We measure what we can. We theorize about what we cannot reach. And somewhere below, the ground continues, quiet and dark, keeping its own record of what happened there. There are places on Earth where the air itself seems to forget the rules. Not in a dramatic way, not with thunder or fire, just quietly in a small valley or along a certain cliff face where the wind does something it should not do, where a light rain, instead of falling straight to the ground, lifts, curls upward, drifts back toward the sky. This is not a trick of the eye. It has been filmed. It has been measured. And yet, the full explanation for why it happens in certain spots and not others just a few meters away remains genuinely open. The phenomenon is sometimes called upward precipitation. In most cases, what people observe is rain or mist being carried sharply upward by a rising column of air. Updrafts, currents of warm air pushing toward the sky, are common enough near cliffs and mountain faces, but certain locations seem to produce them with unusual strength and consistency in places where the terrain does not obviously explain it. Researchers have documented this along particular coastal cliffs in the British Isles, in narrow gorges in parts of Central Europe, and near certain plateau edges in South America. The water does not simply hover. It moves with purpose, climbing the air in thin silver threads. One theory points to something called orographic lift. That is when wind hits a slope or cliff and is forced upward, carrying moisture with it. The rising air cools, and the moisture condenses into mist or light rain. But because the air is still moving upward, the droplets go up before they ever come down. This is a well-understood process in general. What remains less understood is why some locations produce it so reliably, so visibly, and in such narrow, defined columns, while the surrounding land stays dry and still. A competing idea suggests that temperature differences between rock surfaces and the air above them play a larger role than the wind alone. Certain rock types absorb heat during the day and release it slowly at night. That release can create a very localized thermal column. A thin chimney of rising warm air that is strong enough to carry fine water droplets upward for several meters. Some researchers believe these thermal columns are far more common than we notice, and that we simply do not look closely enough at the air above old stone faces and canyon walls. What makes these places feel so quietly strange is the scale. This is not a weather system. It is not a storm. It is a few liters of water moving in the wrong direction, in a space you could walk across in 30 seconds. The strangeness is in the detail. You have to be standing in exactly the right spot, at the right time of day, in the right season, to see it at all. Most people never do. There is something almost meditative about that. The earth is full of these small, precise behaviors, tiny patterns that only appear under very specific conditions. A patch of ground that stays warm all winter. A single boulder that collects dew on one face and never on the other. A narrow gap between two hills where the wind always arrives from the same direction, regardless of where the broader weather is coming from. Scientists who study micrometeorology, the behavior of air and moisture at very small scales within a few meters of the ground, say these local patterns are some of the least studied in all of atmospheric science. The tools to measure them exist. The interest is there, but the sheer number of places on Earth where these small anomalies occur means that most of them have never been formally studied at all. They are noticed by farmers, by hikers, by people who spend long, quiet hours in one place, and then they are passed on as local knowledge, half remembered, never quite written down. There is a certain kind of beauty in that. The idea that the earth is still showing us small things we have not catalogued, that somewhere tonight, in a narrow gorge or along a sea cliff, a few drops of rain are rising instead of falling, and no one is watching. No instrument is recording it. It is simply happening, as it has happened for thousands of years, in a place that has its own quiet logic. We understand the broad strokes of how air and water move together, but the fine details, the reasons why this cliff and not that one, this valley and not the next, those remain genuinely open questions. Small ones, perhaps. But the small questions are sometimes the ones that stay with you longest, turning slowly in the mind as the world goes quiet and still. There are places in the world where the sand itself makes a sound, not a soft whisper of wind moving grains across a dune. Something deeper, something that seems to come from inside the earth. A low, steady moan, or a rumble like distant thunder, rising from the dune face and rolling out across the open desert. People have heard it for thousands of years, and for most of that time, no one could say with any certainty what was making it. The earliest written accounts of singing sand come from travelers crossing the great deserts of Central Asia and the Arabian Peninsula. Some of those accounts are very old. Marco Polo, the medieval explorer who crossed the Gobi Desert in the 13th century, wrote about sounds he heard in the dunes. He described them as the noise of many instruments playing at once. He thought they might be spirits. He was not alone in that belief. For centuries, desert peoples across many cultures interpreted the sound as something beyond the natural world. A voice, a warning, a presence in the sand. That is not a strange conclusion when you hear it for the first time. The sound can be startling. Some dunes produce a tone that holds steady for minutes at a time. Others build slowly and then fade. The pitch can be low enough to feel in your chest, and it happens without warning. Often when the wind picks up and sets the surface of the dune in motion. Early travelers had no framework for it. reached for the explanations that made sense in their time. The first serious attempts to study the sound came much later, in the 19th century. European explorers and naturalists began to document the phenomenon in a more systematic way. They noted which dunes sang and which did not. They tried to describe the conditions that seemed to trigger it. Some thought the sound was caused by electricity building up in the dry air. Others believed it had something to do with the hollow spaces beneath the dune, like a drum resonating from below. These were reasonable guesses for the tools and knowledge of the time. But they were guesses. One of the more careful early investigators was a British explorer named R.A. Bagnold, who spent years studying desert dunes in the early 20th century. Bagnold was a soldier and a scientist both, and he had a methodical mind. He measured dunes. He recorded their shapes and their movements. He listened to them. He concluded that the sound was produced by the sand grains themselves, moving against each other in a very specific way. He called it a kind of avalanche, a slow cascade of grains down the slip face of the dune, generating vibration as they went. His work was careful and important, but it did not fully settle the question, because even now, researchers do not entirely agree on the mechanism. One leading idea is that the grains vibrate in sync, like a choir finding the same note, and that this synchronized motion amplifies the sound into something audible and sustained. The grains need to be a specific size, and they need to be very dry, and they need to be coated in a particular way, smooth and round from long years of wind polishing. When those conditions align, the dune can sing. But another school of thought holds that the shape of the dune itself matters just as much as the grains. Some researchers believe the dune acts as a resonating body, that its curved face and its depth and its angle to the wind all combine to shape the tone. Under this view, two dunes made of identical sand might produce different sounds simply because of their form. The grain theory and the shape theory are not entirely opposed, but they emphasize different things, and the debate between them is still active. What makes this history interesting is how long it took for the question to even be asked in a scientific way. For most of human history, the singing dunes were simply a feature of the desert, noted and wondered at, and folded into local story and belief. The instruments needed to measure grain vibration and acoustic resonance did not exist until the 20th century. The question could not be answered before the tools arrived. And even with those tools, the answer remains incomplete. There are singing dunes on every major desert continent. Each one has its own pitch, its own character, its own conditions. Some sing only in certain seasons. Some have gone quiet in recent decades, possibly because of changes in moisture or the movement of sand. Why some dunes sing and others do not, even when they look nearly identical, is still a question without a clean answer. The desert holds the sound close and gives up its secrets slowly. There is a small island in the Mediterranean Sea that appears, stays for a while, and then quietly disappears beneath the water again. It has done this more than once. Sailors have reported it. Governments have claimed it. And then the sea swallows it, and the argument becomes moot. The island is called Ferdinandia, or Graham Island, depending on which country you ask. It sits in the waters between Sicily and the coast of North Africa, above a shallow underwater volcano. When the volcano pushes upward with enough force, new rock breaks the surface. An island is born. Then the waves and the wind wear it down, and the sea reclaims it. This has happened at least 4 times in recorded history. Each time, the island rose and drew attention. Each time, it sank again before anyone could settle the question of who owned it. The geology is not mysterious in the broad sense. Volcanic islands form this way. But what makes Ferdinandia strange is how it sits at the edge of what we can predict. Scientists can monitor the underwater volcano. They can watch the seafloor rise and fall, but the exact timing, the exact height the island will reach, and how long it will last, those things remain genuinely difficult to forecast. What surprises most people is that this is not rare. There are places around the world where land appears and disappears on a timescale that feels almost alive. Some of these are volcanic, like Ferdinandia. Others form from sand and sediment, carried by rivers and currents, piling up until a sandbar becomes an island. Then then washing away again in a single strong storm. The Bay of Bengal holds islands like this. They form, they are mapped. People sometimes settle on them, and then a cyclone comes through, and the island is simply gone. One island off the coast of Alaska appeared after a series of underwater earthquakes in the early 20th century. It was there long enough to be charted. Then it was not. The seafloor had shifted, and whatever had pushed the land upward had relaxed again. The counterintuitive part is that solid ground, the thing we think of as permanent and reliable, is in some places neither of those things. Some researchers point to a process called isostasy, which describes how the Earth's crust floats on the softer rock below, rising and sinking in response to weight. When a thick glacier sits on land for thousands of years, the crust beneath it slowly sinks. When the glacier melts, the land slowly rises back. This is happening right now in Scandinavia and parts of Canada, where the land is still rebounding from ice that melted more than 10,000 years ago. In some places, the rise is measurable year by year. In others, the rate is so slow it can only be seen across centuries. But isostasy does not fully explain every island that comes and goes. Some of these places seem to shift faster than the models predict. Others appear in locations where the underlying geology does not obviously support that kind of movement. One theory is that pockets of trapped gas or superheated water beneath the seafloor can cause sudden, temporary uplifts. Another is that sediment dynamics, the way sand and silt move through ocean currents, are more complex and more variable than current models capture. Neither theory has been confirmed as the complete answer. There is something quietly strange about the idea that a place can exist and then not exist. We tend to think of geography as fixed. We draw maps and trust them. But the map of the world is, in a very slow and patient sense, always being redrawn. New islands emerge from the sea near Iceland every few decades. Old ones erode and vanish. The shorelines of continents shift over centuries. The land we stand on is not a finished thing. What makes the coming and going islands feel like a surprise is that they compress that change into a human timescale. Instead of millions of years, the change happens in months or years. A place that was not there last decade is there now. A place your grandparents knew is underwater. The Earth is not being dramatic about this. It is simply doing what it has always done, which is change, slowly, and then sometimes quickly, without asking permission or giving warning. The question of which islands will appear next, and which ones currently on maps will quietly vanish, remains genuinely open. Scientists watch the seafloor with sonar and satellites. They track volcanic activity and sediment flow, but the Earth keeps a few surprises in reserve. Some of the land that will exist in 100 years does not exist yet. Some of the land that exists tonight will not be there to find. There are places on Earth where a ball will roll uphill, where a car left in neutral will creep forward against the slope, where water in a thin stream appears to flow the wrong way. These places have names: gravity hills, magnetic hills, mystery spots. And for a long time, people who visited them came away genuinely unsure what they had witnessed. The strange thing is, these places are connected to something much larger. They sit at the crossing point of several forces at once: geology, light, perception, and the invisible pull of the Earth itself. Understanding why they feel so wrong means pulling on threads that reach deep into the ground and far across the sky. Gravity, as most of us picture it, is steady and even. It pulls everything straight down toward the center of the Earth. But the Earth is not a perfect, smooth sphere. It bulges slightly at the equator. It dips and rises in ways that satellites can now measure very precisely. And the rock beneath our feet is not the same everywhere. Dense rock pulls harder than light rock. A mountain of heavy stone can tug a plumb line. A simple, hanging weight, slightly sideways. This has been measured. It is real. So the first theory about gravity hills is simple. The ground beneath them is unusually dense or unusually shaped, and it bends the local pull of gravity just enough to create a small but detectable difference. One team of researchers found that certain so-called gravity anomalies, places where the pull is measurably stronger or weaker than expected, do cluster near some of these strange spots. The connection is not proven in every case, but it is worth sitting with. The second theory is quieter and, in some ways, more interesting. It says the ground is not doing anything unusual at all. It says our eyes are doing the work. When the trees around a slope all lean slightly in one direction, when the horizon is hidden by hills, when every visual cue around us points the wrong way, our brains recalibrate. They decide, based on everything they can see, which way is down. And sometimes they get it wrong. A slope that rises at 3 degrees can look like it falls at 3 degrees if the surrounding land tilts the other way. The ball rolls downhill. We see it roll uphill. Both things are true at once. This is called a visual illusion caused by a false horizon. Researchers have tested it carefully at several famous gravity hills. They bring precise leveling tools. They measure the actual slope. In many cases, not all, but many, the slope runs exactly the way physics would predict. The car rolls downhill. The water flows downhill. The mystery in those cases lives entirely inside the human mind. But here is where the connection to other systems becomes interesting. The places where the visual illusion works best are often the same kinds of places where other strange reports cluster. Valleys with unusual tree growth, hillsides near old fault lines, regions where the rock beneath is layered in ways that trap gases or channel groundwater in odd directions. It is as if the conditions that make a place look strange are also the conditions that make it feel strange in other ways. Some researchers wonder whether low-frequency vibrations from underground water or shifting rock might subtly affect how people feel in certain spots, not dramatically, not in ways that are easy to measure, but enough to add a layer of unease to an already disorienting view. The body picks up signals the conscious mind does not register. A faint hum through the soles of the feet, a barely perceptible change in air pressure. These things are not proven causes. They are open questions. What ties all of this together is the idea that Earth systems are never truly separate. The rock affects the gravity. The gravity affects the water. The water shapes the land. The land shapes the trees. The trees shape what the eye believes, and the eye shapes what the mind decides is real. Each layer feeds into the next, quietly, over long stretches of time. A gravity hill is not just a trick of the eye or a quirk of dense rock. It may be both at once. It may be neither. The honest answer is that researchers have explained some of these places and left others genuinely open. The measurements do not always agree. The theories do not always fit. And that gap between what we can measure and what we experience standing on that strange, tilted ground is itself a kind of mystery worth holding onto. The earth is full of places where our instruments and our senses tell different stories. Tonight, that is enough to wonder about. There are rivers in this world that run colors you would not expect from water. Deep red, bright orange, pale white, even black. And the reasons behind those colors are not always as simple as they first appear. Some rivers carry so much dissolved iron that their water looks like rust. The Rio Tinto in southern Spain is one of the most striking examples. It runs a deep, vivid red for miles through dry hills and pale rock. The color comes from iron and sulfur compounds leaching out of ancient mineral deposits in the ground. The water is also highly acidic, far more acidic than most rivers anywhere on Earth. For a long time, people assumed nothing could live in it. That assumption turned out to be wrong. Tiny microbes, organisms too small to see, thrive in the Rio Tinto's acid waters. Some researchers now wonder whether those microbes are partly responsible for the river's color, not just passengers in it. The relationship between the water, the minerals, and the life inside it is still being studied. Which came first, the acid or the microbes, is not a settled question. What makes this especially interesting is that the Rio Tinto has looked this way for a very long time. Ancient mining activity in the region goes back thousands of years, but the river's chemistry appears to predate human mining by a wide margin. Some geologists believe the acidic conditions existed long before people arrived. Others think centuries of mining accelerated what was already a slow, natural process. The two ideas are not mutually exclusive, but the balance between them is hard to measure. Rivers change color for many different reasons, And not all of them involve minerals. Some rivers run milky white because of glacial flour, a fine powder of crushed rock that glaciers grind out as they move. The powder stays suspended in the water and scatters light in a way that makes the river look almost luminous. Glacial rivers in places like Iceland and the Canadian Rockies can shift from pale gray to brilliant turquoise depending on the season, the temperature, and how much meltwater is flowing. The color is not fixed. It moves with the glacier's rhythm. Other rivers run dark, almost black, because of tannins, natural compounds that leach from decaying leaves and plant matter in the surrounding forest. The Rio Negro in South America is one of the largest dark water rivers on Earth. Its water is clear but deeply stained, like very strong tea. When the Rio Negro meets the lighter-colored Amazon, the two rivers flow side by side for miles without fully mixing. The boundary between them is sharp and visible from above. Scientists understand the basic chemistry behind this, but the precise conditions that keep the two rivers separate for so long are still being examined. Water temperature, density, and flow speed all seem to play a role. The colors of rivers are also changing in ways that concern researchers. Some rivers that once ran clear are now running orange or brown where they did not before. In parts of Alaska and northern Canada, rivers that were clear for as long as anyone can remember have begun turning rust-colored over the past few decades. The leading explanation involves permafrost, the layer of permanently frozen ground beneath the soil. As temperatures rise, that frozen layer thaws. When it thaws, it releases minerals and iron that had been locked inside it for thousands of years. The iron oxidizes in the water and turns it orange. This is a relatively recent observation, and scientists are still working to understand how widespread it might become. What is striking about all of these rivers is that their color is a kind of message. It tells you something about what the land around them is made of, what is dissolving, what is changing. A river's color is never random, but reading that message clearly is harder than it looks. The same orange tint can come from iron-rich bedrock, from thawing permafrost, or from runoff after a wildfire. Separating those causes requires careful measurement over long stretches of time. And rivers do not stay the same color forever. They shift with the seasons. They shift with the decades. They shift as the land around them changes. A river that runs red today may have run clear 1,000 years ago. A river that runs clear today may not always. The earth is always moving its minerals around, always dissolving and depositing, always rewriting the chemistry of its water. The colors are a record of that slow, patient work. We are only beginning to learn how to read them. There are places on Earth where the ground holds its secrets in plain sight. You can walk across them, stand in the middle of them, and still not see what is there. It is only when light falls at a certain angle, low and long, early morning or late afternoon, that the land reveals something older than memory. Shadows stretch across the soil. Shapes appear, and for a moment, the world looks like it is trying to tell you something it has been holding for a very long time. This is how many ancient structures are first noticed. Not by digging, not by instruments, by light. When the sun sits low on the horizon, it grazes across the surface of the earth at a shallow angle. Archaeologists call this raking light, and it does something that midday sun cannot. It throws even the smallest rise or hollow into sharp relief. A ridge that is only a few inches tall casts a shadow several feet long. A shallow ditch, long since filled with soil, becomes a dark line cutting across a field. Shapes emerge that were invisible an hour before. Circles, rectangles, long straight lines that do not follow the natural curves of the land. Some of these shapes are the outlines of structures that have been swallowed by the earth over centuries. Walls crumble, roofs fall, soil drifts in, roots push through. Rain washes sediment across the ground. Given enough time, even a large building can become a gentle undulation in a field, indistinguishable from a natural hill, unless the light catches it just right. What makes certain places strange is not that they contain buried structures. That is common enough. What makes them strange is the scale of what the light reveals, and how little we understand about who built these things, or why, or how they came to be forgotten. so completely. In parts of the Middle East, aerial photographs taken in low morning light have shown vast geometric patterns stretching across the desert floor. Some of these patterns are enormous, covering areas larger than several city blocks. They appear to be ancient stone walls arranged in shapes that some researchers believe were used to guide animals during hunts. Others think the shapes may have had a ceremonial purpose. The evidence is incomplete, and the two ideas sit side by side without resolution. These structures are sometimes called the works of the old men, a name given to them by local communities who knew they were old, but did not know who made them. The light that reveals them is the same light that hid them. For most of the day, the sun is too high. The shadows are too short. The shapes disappear back into the desert. It is only at the edges of the day, when the light is almost horizontal, that the old geometry comes back. Something similar happens in other parts of the world. In parts of the Amazon, researchers using a technology called LiDAR, a method that uses pulses of laser light to map the ground beneath dense forest cover, have found the outlines of enormous earthworks hidden under centuries of vegetation, causeways, enclosures, platforms, structures that suggest large, organized communities once lived in places that are now deep jungle. The light, in this case, is not sunlight grazing across a field. It is laser light bouncing back from the forest floor, read by instruments that can separate the signal of bare earth from the signal of leaves and branches. What those structures mean, who built them, and how those communities eventually disappeared are questions that remain open. Some researchers believe the Amazon was once home to far more people than anyone assumed. Others argue the evidence is still too thin to support such large claims. The debate continues. There is something quietly moving about the idea that the land holds these shapes, patient and still, waiting for the right kind of light to make them visible again. A wall that has not been seen in 1,000 years. A road that no one has walked in centuries. The earth does not erase these things entirely. It covers them, and sometimes, on a clear morning when the sun is still close to the ground and the shadows are long and blue, they come back. question is not simply what these structures are. The question is what else is still hidden. How many shapes are lying just beneath the surface of ordinary-looking fields and forests, waiting for the angle of light to shift just enough to give them away. The earth is patient. It keeps its shapes. We are still learning how to look. There are places on Earth where the animals go quiet. Not the ordinary quiet of a forest at midday, when birds rest in the shade and insects pause in the heat. This is a different kind of quiet, a chosen quiet, a quiet that seems to come from the animals themselves, as though something in the ground or the air has told them to stay back. Farmers have noticed it for centuries. Shepherds in parts of Europe have described certain hillsides where their dogs will not follow. Horses that cross open fields without hesitation will stop at an invisible line and refuse to go further. Dogs lower their heads. Cattle turn away. The behavior repeats, season after season, in the same locations. And for a long time, no one had a good explanation. One idea is that animals are sensing infrasound. Infrasound is sound that falls below the range human ears can detect. We cannot hear it, but we can sometimes feel it. A low pressure in the chest, a vague unease we cannot name. Some animals, though, are far more sensitive to these low frequencies than we are. Elephants communicate across many miles using infrasound. Certain birds navigate using it. And some researchers believe that geological stress, the slow grinding of rock layers deep underground, can produce infrasound that animals pick up long before any instrument does. The idea is that certain locations sit above fault lines, or above pockets of gas, or above rock formations that channel and amplify these low vibrations. The ground hums at a frequency we cannot hear. The animals can, and they choose not to enter. But not everyone agrees that infrasound is the whole answer. Some researchers point to electromagnetic fields instead. The Earth generates magnetic fields, and those fields are not perfectly even. They shift and pool in certain areas, especially near mineral deposits or underground water. Some animals are known to sense magnetic fields. Certain birds use them to to navigate. Cows, in some studies, tend to align their bodies along magnetic north when they graze. If an animal can sense the magnetic field of the planet, it might also sense when that field behaves strangely in a particular place. There are locations where the magnetic field is measurably irregular. Some of these locations overlap, at least roughly, with places where animals show avoidance behavior. Whether that overlap is meaningful or coincidental is still an open question. Then there is the possibility of smell. The Earth breathes out gases through cracks in its surface. Radon is one of them, a naturally occurring gas that seeps up through rock and soil in certain areas. Some volcanic regions release sulfur compounds. Methane rises through wetlands and through faults in dry ground. Humans can detect some of these gases at high concentrations, but animals, with their far more sensitive noses, might detect them at levels we would never notice. A dog that refuses to cross a hillside might simply be smelling something we cannot. What makes this harder to study is that these explanations are not mutually exclusive. A place might produce infrasound and unusual magnetic readings and trace gas emissions all at once. Separating the causes is difficult, and the animals, of course, cannot tell us which signal they are responding to. There is also the question of learned behavior. Some researchers suggest that animal avoidance of certain places might be partly cultural, passed from older animals to younger ones over generations. A herd that lost members near a particular bog or cliff edge might develop a tradition of avoidance that outlasts the original danger. The knowledge travels without language. It travels through behavior, through hesitation, through the way an older animal stops and the younger ones stop with it. This idea is harder to test, but it raises a quiet and interesting possibility. Some of the places animals avoid might have been genuinely dangerous in the past, even if the danger has faded. The avoidance persists like a memory held in the body of the herd. What we are left with is a set of overlapping possibilities and no single clean answer. The infrasound theory has some support. The electromagnetic theory has some support. The chemical theory has some support. The learned behavior theory has some support. None of them on its own explains every case, and the cases themselves are not always well documented because, for most of human history, a shepherd noting that the dogs would not follow was not considered a scientific observation worth recording. The ground hums, the field shifts, the air carries something faint and unreadable, and the animals, in their quiet way, know something we are still trying to understand. There are places on Earth where ice refuses to follow the rules. High on the slopes of certain equatorial mountains, glaciers cling to rock faces even where the air around them is warm enough to melt them. In some desert regions, pockets of ancient ice sit buried beneath the ground, surviving in places where the surface temperature climbs well above freezing for months at a time. These are not small anomalies. They are measurable, documented, and still not fully explained. And what makes them stranger still is that when scientists look closely, they find a kind of quiet mathematics underneath the mystery. Ice, at its most basic, follows simple rules. Water freezes at 0 degrees Celsius. It melts when heat is added. The relationship between temperature and the state of water is one of the most reliable patterns in nature. Children learn it early. Scientists rely on it constantly. So when ice appears where the numbers say it should not, the question is not just geological. It is almost mathematical. Something in the equation is missing. One of the most studied examples sits on the slopes of Mount Kilimanjaro in Tanzania. The glaciers there have been shrinking for over a century. That part is well documented. But certain sections of the ice persist in ways that confuse the models. Some researchers point to the unusual dryness of the surrounding air. Ice, they argue, can sublimate, meaning it passes directly from solid to vapor without melting. And in very dry air, this process can actually preserve a glacier's core, even as its edges retreat. The ice does not melt so much as it slowly disappears into the air. But other researchers question whether sublimation alone explains the patterns they observe. The debate is still open. Then there are the ice caves. In parts of the American Southwest, in the lava fields of New Mexico and Arizona, Ancient tubes of cooled volcanic rock hold ice year-round. The surface above them bakes in summer sun. But deep inside the tubes, temperatures stay below freezing. One theory holds that cold winter air sinks into the caves and becomes trapped, unable to escape because warm air rises and never pushes it out. The cave acts like a natural cold trap. Another idea suggests that the geometry of the rock itself, its thickness, its color, its position on the slope, creates a kind of insulation that no simple temperature reading can capture. Both ideas have supporting evidence. Neither fully accounts for every cave that behaves this way. What draws scientists back to these places again and again is the elegance of the underlying question. Ice is simple. The math of freezing and melting is clean. And yet the earth finds ways to complicate it. There is something almost beautiful in that. The planet does not break the rules of physics. It finds arrangements of rock and air and shadow that use those rules in unexpected combinations. The answer, when it comes, will almost certainly be mathematical. It will involve angles of sunlight, rates of airflow, the specific heat capacity of different kinds of stone. These are not mysterious forces. They are precise, measurable quantities. The mystery is simply that we have not yet arranged them in quite the right order. In Greenland and parts of Antarctica, researchers have found pockets of ancient ice that date back hundreds of thousands of years. This ice is extraordinarily old. It holds tiny bubbles of air from a world that no longer exists. The fact that it survived so long is itself a kind of puzzle. The ice should have flowed, compressed, and eventually been lost to the slow movement of glaciers. That some of it remains intact suggests that local conditions, the exact shape of a valley, the precise angle of a ridge, created a shelter so effective that time itself seemed to slow inside it. Whether those conditions can be fully modeled is still an open question. There is a phrase that scientists sometimes use when a measurement does not match a prediction. They call it a residual. It is the small number left over after the known forces have been accounted for. In the case of ice that does not melt, the residual is not small. It is large enough to notice, large enough to study, and large enough to suggest that something real and physical is happening that the current models do not yet capture. The numbers are all there, waiting. The angles, the temperatures, the flow rates, the depths. Somewhere in that arrangement of figures is an answer. It may be a simple one. Many great mysteries turn out to have simple answers once the right measurement is finally taken. But for now, the ice sits quietly in its impossible places, cold and patient, keeping its own counsel. There are sounds the earth makes that no one has fully explained. Not the crack of thunder, not the groan of a settling glacier. Those sounds have answers. The sounds we are thinking about now are quieter, stranger, and far more stubborn. They arrive without warning. They have no clear source, and in some cases, they have been heard by hundreds of people across wide stretches of land, all at the same time. One of the most studied is a low, steady hum. It sits at the very edge of what human ears can detect. Some people describe it as a diesel engine idling far away. Others say it feels more like a pressure inside the skull than a sound in the air. Researchers have recorded versions of this hum in coastal towns, in desert regions, and near certain mountain ranges. The recordings are real. The vibrations are measurable. What causes them is still genuinely open. One theory points to the ocean. Waves do not just crash on shores. They also press down on the seafloor in long, slow pulses. Some researchers believe these pulses travel through the rock itself, spreading outward like ripples, and that what certain people hear is the faint echo of that pressure moving beneath their feet. The ocean, in this view, never stops singing. Most of us simply cannot hear it, but that theory does not explain everything. The hum heard in some inland locations does not match the patterns you would expect from ocean-driven vibrations. The timing is wrong. The frequency shifts in ways that ocean pressure alone cannot account for. So some researchers have proposed a second possibility, that pockets of gas or fluid deep underground move through narrow channels in the rock, and that this movement creates a low resonance. The way blowing across the mouth of a bottle creates a tone. The earth in this version is full of hidden chambers that occasionally vibrate. Neither explanation has been confirmed. Both remain working ideas. There are other unexplained sounds too. In certain desert regions, sand dunes produce a deep, resonant booming when the surface grains shift in large numbers. This one has a partial explanation. Researchers believe the sound comes from layers of sand moving against each other at just the right speed, with just the right grain size, creating a kind of natural instrument. But the conditions that trigger it are not fully understood. Some dunes boom often. Others, with nearly identical sand, never make a sound. The difference between a singing dune and a silent one is still not clear. Then there are the sounds that come from the sky. Low rumbles with no storm attached. A distant roar that fades before anyone can locate it. These have been reported from flat plains, from dense forests, and from open coastlines. Some researchers suspect they are connected to pressure changes in the upper atmosphere, that layer of air sitting far above the weather we experience. Others think they may be linked to movements in the ground itself, vibrations too slow and too deep to feel, but somehow audible in certain conditions. What makes all of this harder to study is that sound behaves strangely near the ground. It bends around hills. It travels farther at night when the air is cooler and denser close to the surface. A sound made miles away can arrive clearly in one valley and be completely absent in the next. This means that even when a sound is recorded, tracing it back to its origin is genuinely difficult work. And here is where the fragile balance of the question becomes clear. The Earth is a system of moving parts, all pressing against each other with enormous force. Rock presses on rock. Water presses on rock. Air presses on water. Gas presses outward from below. Each of these pressures is enormous. Each of them creates vibration. Most of that vibration is absorbed, scattered, or simply too slow for human senses. But occasionally, in certain places, under certain conditions, something aligns just right. The vibration finds a path. It reaches the surface. It becomes a sound. Whether that sound is the ocean breathing through the rock, or gas moving through deep channels, or something else entirely, is still an open question. The instruments exist to measure it. The recordings exist to study. But the full picture has not come together yet. The earth is not silent. It has never been silent. It hums and booms and resonates in frequencies most of us pass through our whole lives without noticing, that we are only now beginning to listen carefully, and that we still cannot explain what we hear. Feels like one of the quieter wonders of this strange old world. There are places on this earth where something feels quietly, persistently off. Not in a frightening way. More like the feeling of a clock that runs just slightly slow, or a room where the afternoon light seems to linger longer than it should. Scientists have names for many of these places. They have measurements, instruments, careful records. And yet, even with all of that, certain locations hold onto something that the numbers alone cannot quite capture. Take the area around some of the world's ancient stone circles and megalithic sites. Those great rings of standing stones built by people whose names we will never know. Researchers have measured the electromagnetic fields, the soil composition, the acoustic properties of these places. Some sites produce unusual readings on sensitive instruments. Low-frequency sound waves, called infrasound, have been detected at several of these locations. Infrasound sits below the range of human hearing, but the body can still feel it. Some researchers believe that infrasound can produce a faint sense of unease, or even a feeling that time is passing strangely. One theory holds that the stones themselves, or the landscape around them, naturally channels these low sounds in ways that affect human perception. But another group of researchers is more cautious. They point out that infrasound is common in many places that feel perfectly ordinary. Wind moving over hills, ocean waves breaking far away. Even large buildings can generate it. The question of whether these ancient sites produce something genuinely unusual, or whether we simply notice it more because we expect to, remains open. Expectation is a powerful thing. The mind is very good at finding what it is already looking for. Then there are places where human timekeeping itself seems to behave strangely. In certain deep caves, volunteers have spent weeks without clocks, without sunlight, without any any external cue about the passing of hours. Their internal rhythms, the biological clocks that govern sleep, hunger, and alertness, slowly drifted. Some volunteers believed far less time had passed than actually had. Others felt that days had stretched into something longer and softer. The caves did not change time, of course, but they revealed how fragile our sense of time really is when the usual anchors are removed. Some researchers wonder whether certain landscapes above ground might do something similar in subtler ways. Dense forests with no clear sky, deep valleys where the sun appears for only a few hours each day, fog-bound coastlines where the light is always diffuse and directionless. These environments don't alter clocks, but they may alter the internal experience of duration in ways that are still being studied. The science of how place affects time perception is genuinely young. The Richat structure in Mauritania, that enormous circular formation in the Sahara, sometimes called the Eye of the Sahara, sits in one of the most isolated stretches of desert on Earth. People who have traveled there on foot describe a strange quality to the experience of moving through it. The scale is so vast that progress feels almost impossible to measure. You walk for an hour, and the landscape looks nearly the same. The rings of eroded rock seem to repeat. Some travelers have described a feeling of suspension, as if the ordinary markers of forward movement had dissolved. Geologists explain this as a simple function of scale and visual monotony. The structure is roughly 50 kilometers across. Of course, it feels endless, but the subjective experience of those who have been there is harder to quantify. There is a broader question underneath all of this. We tend to think of time as something fixed and external, something that ticks along at the same rate regardless of where we stand. But human experience of time is deeply tied to place, to light, to sound, to the subtle signals the environment sends to the body. Some landscapes seem to slow that experience. Others seem to compress it. The reasons are not always clear. What remains genuinely unsolved is whether certain places have physical properties, acoustic, electromagnetic, or otherwise, that consistently alter time perception in measurable ways. A handful of researchers are working on this question. The tools for measuring subjective experience are still quite limited, and the places themselves are often remote, difficult to study, and full of variables that are hard to control. So the question sits open, as so many of the best questions do. Not because no one has tried to answer it, because the answer, if there is one, keeps slipping just slightly out of reach, like a sound heard at the edge of sleep, present and real, and not quite graspable. Some places seem to hold time differently. Whether that is the place, or the mind, or something quietly shared between them, no one has yet been able to say. There is a forest in Poland where the trees grow crooked. Every trunk bends at the base, curves toward the north, and then straightens again as it rises. No one planted them that way on purpose. No storm bent them all in the same direction on the same night. They simply grew like that, and the reason why is still an open question. But here is something even quieter to sit with. Those trees are alive right now. They are still growing. And in 1,000,000 years, they will be gone, replaced by something we cannot yet picture. That is the strange gift of thinking about the future. It loosens the grip of the present. It reminds you that every unexplained place on Earth is also a place in motion, always becoming something else. The crooked forest will not stay crooked forever. Trees fall, soil shifts. The seeds those bent trees drop may grow perfectly straight, or they may curve again in ways no one expects. Some researchers wonder whether the bending was caused by heavy snow pressing on young saplings during a single hard winter long ago. Others suggest a now forgotten farming technique shaped the trunks deliberately, perhaps to grow curved wood for boat building or furniture. The evidence for either idea is thin. What we do know is that the forest holds its shape for now, but the land beneath it does not stand still. In 1,000,000 years, the ground under Poland will have moved. The tectonic plates, those vast, slow slabs of rock that carry the continents, drift at roughly the speed a fingernail grows. That sounds impossibly slow, but given enough time, it adds up to enormous distances. The land that holds the crooked forest today will be somewhere else entirely. the forest itself will be long gone, pressed into the rock record, or dissolved, or carried away by a river that has not yet formed. This is true of every strange place we have visited in this long, quiet night. The sailing stones of Death Valley rest on a dry lake bed that was once full of water and will one day be buried under sediment. The Moeraki boulders on the coast of New Zealand are slowly being worn away by the sea. The stone spheres of Costa Rica, so perfectly round and so mysterious in their origin, sit in soil that is always moving, always eroding. In a few million years, they may be unrecognizable. And yet, new strange places will form. That is the part worth holding onto as you rest. The earth does not stop making things. It makes them constantly, in ways we do not always predict. Pingos, those dome-shaped hills of frozen ground that push up from the Arctic tundra, are forming right now in places that were flat a century ago. As the climate shifts, some researchers believe entirely new landforms will appear in regions where permafrost, the deep frozen ground beneath the surface, begins to thaw and collapse. The craters left behind may look, to some future observer, just as mysterious as the holes we puzzle over today. The forests of the future may walk in a different sense entirely. Not the trees themselves, but the forests as a whole. A forest moves over centuries as trees die on one edge, and seeds take root on the other. Given enough time and a changing climate, a forest can migrate hundreds of miles from where it stood before. The trees do not know they are walking, but from far enough above and far enough in time, that is exactly what it looks like. One idea in ecology, the study of how living things relate to their environment, is that forests are not fixed communities, but slow rivers of life, always flowing toward conditions that suit them. If that is true, then every forest we see today is mid-journey, somewhere between where it was and where it is going. The crooked forest of Poland is no different. It is a moment in a very long story. 1 billion years from now, the continents will have rearranged themselves again. Some models suggest they may merge into a single landmass, the way they have done before in Earth's deep history. The strange places we know, the humming valleys, the singing deserts, the lakes that glow will be buried, transformed, or simply erased, but the processes that made them will still be running. Water will still move through rock. Ice will still push against soil. Gas will still rise through the ground. The earth will still be making mysteries. It has never stopped. It will not stop when we are gone. Whatever walks through those future forests, if anything does, will look at the land and wonder why it looks the way it does. And the answer, as always, will not come easily. There are places on this earth where the air itself feels different. Not warmer or colder, not wetter or drier, but somehow changed in a way that is hard to name. People who visit these spots often say the same thing. They say the air feels thick, or thin, or charged, or still in a way that ordinary air is not. And science, for all its careful tools, has not fully explained why. Some of these places sit at high altitude, where the atmosphere grows thin, and the sky above turns a deeper shade of blue. The air there carries less oxygen, and the body notices. But that is not the whole story. Certain high valleys in the Andes, certain plateaus in Tibet, certain ridges in the Ethiopian highlands carry a quality that altitude alone does not account for. Travelers describe a kind of quiet that seems to press inward, a stillness that feels less like the absence of wind and more like something present. One idea is that the geology beneath these places shapes the air above them. Rock that contains certain minerals, particularly those rich in iron or quartz, may interact with the atmosphere in ways that are still being studied. Some researchers have suggested that piezoelectric effects, the tiny electrical charges that certain crystals produce when they are squeezed or stressed, could alter the local air in subtle ways. The theory is not settled. Others point out that the human body is simply very sensitive to small changes in air pressure, humidity, and ion concentration, and that our minds fill in the rest with feeling. The question of ions is its own open chapter. Near waterfalls, near the ocean, near places where water crashes against stone, the air tends to carry more negative ions, which are oxygen atoms with an extra electron. Some studies suggest that breathing air rich in negative ions affects mood and alertness. the research is still incomplete and the results are not consistent, what is more interesting for our purposes is that certain dry, still places seem to carry an unusual concentration of positive ions, and people in those places often report feeling uneasy or heavy. The Santa Ana winds of California, the Fun winds of the Alps, the Cherev winds of the Middle East, all carry high positive ion counts, and all have been linked in folklore and in some early research to feelings of restlessness or unease. Whether the ions cause the feeling or whether something else is at work remains an open question. Then there are the places where the air carries sound in unexpected ways. Sound needs air to travel, and air is not a uniform thing. It bends and pools and channels depending on temperature, humidity, and the shape of the land. In certain desert valleys, a whisper spoken at one end can be heard clearly at the other, hundreds of meters away. Ancient builders may have understood this. Some researchers wonder whether certain stone structures were placed deliberately in spots where the acoustics of the landscape were already unusual, where the air already gathered and carried sound in ways that felt remarkable. We do not know. The evidence is suggestive, but not complete. There is a wider thought worth sitting with here. The air itself is ancient. The oxygen in each breath you take tonight has been breathed before by creatures that lived millions of years ago, by forests that no longer exist, by oceans that have long since changed their shape. The atmosphere is not a fixed thing. It has shifted and changed across deep time, and the air above any given place on Earth carries a history that we are only beginning to read. When a place feels strange, when the air seems different, we are perhaps sensing something real, some local variation in a system so vast and so old that our instruments have only just begun to measure it. The strange places of this earth are not separate from us. They are made of the same elements, the same ancient materials, the same slow processes that made the ground beneath your bed and the air in this quiet room. The calcium in stone is the calcium in bone. The iron in deep rock is the iron in blood. When we wonder about a place that science has not yet explained, we are wondering about ourselves, about the same forces that built us. working in a different arrangement, in a different corner of a very old world. The air in those strange places is still moving tonight, slowly, quietly, over stone and sand and water, carrying its ions and its history and its open questions out across the dark. We breathe the same air. We share the same mystery. And so we arrive at the end of our long, quiet walk across this strange and beautiful planet. We have moved through humming forests and singing deserts. We have stood at the edge of craters that glow orange in the dark. We have traced the slow paths of stones that cross dry lake beds without a single hand to push them. We have looked down into caves that whisper and up at lights that have no clear source. And through all of it, the same quiet truth has followed us like a shadow. The earth has not finished explaining itself. That is not a failure of science. It is something closer to an invitation. Every place we visited tonight sits at the edge of what we understand. The Richat structure rises from the Saharan sand in perfect rings, and researchers still debate whether it was born from a meteor or from forces deep inside the rock itself. The crooked trees of Poland bend in their silent curves, and no one has settled the question of what shaped them that way. The stone spheres of Costa Rica sit in their clearings, smooth and patient, and the people who made them left no written record of why. These are not small gaps. They are wide open spaces in our knowledge, and they have been there for decades. Some of them may be there for decades more. There is something peaceful in that, if you let yourself feel it. The planet is older than almost anything we can imagine. It has been turning for roughly 4.5 billion years. The mountains we think of as ancient were, to the Earth, recent. The forests we call old are barely a breath in geological time. And in all that vast, slow turning, the Earth has made things we still cannot fully read. It made places where compasses drift and instruments give strange readings. It made ice that refuses to melt in summer. It made rivers that run red and yellow and blue, colored by minerals and chemistry we are still mapping. It made holes in the ground so deep that the bottom has never been confirmed. It made islands that rise from the sea and then sink again, as if the ocean is simply thinking out loud. We We are very small in the face of all that. And tonight, that smallness feels like a comfort rather than a worry. Think of the planet right now as you rest. The ocean is moving in the dark. Long, slow swells cross the Pacific, rolling under a sky full of stars. On a dry lake bed somewhere in the American desert, a flat stone sits perfectly still in the cool night air, waiting for the thin ice and the wind that will, one day, carry it a little further across the pale ground. In a forest in Poland, the bent trees stand in their rows, quiet and curved, holding whatever secret shaped them a long time ago. In Laos, the great stone jars rest in their fields under the moon. In New Zealand, the Moeraki boulders sit half buried in the sand where the tide pulls back, round and gray and ancient. In the Sahara, the rings of the Richat structure spread outward across the rock, visible from far above, patient as they have always been. None of these places are waiting for us to solve them. They were here long before we arrived, and they will be here long after. They do not need an answer tonight. They are simply here, existing in the quiet way that the earth exists, slowly, steadily, without urgency. Science will keep asking. Researchers will keep returning to these places with better tools and new ideas. Some mysteries will soften over time and give up a little of what they hold. Others may stay open for longer than any of us will live to see. That is the honest truth, and it is a gentle one. For now, the planet turns. The ocean breathes. The stones are still. The forests are quiet. The ice holds its shape in the cold mountain air, and the deep caves are dark and calm. And somewhere a light moves slowly across the surface of a lake, and no one is quite sure what it is. That is enough. That is more than enough. You have traveled far tonight, across deserts and forests and deep cold water, across questions that have no clean ending. You can set all of it down now. The earth will keep its mysteries safe until morning. You do not need to carry them into sleep. Rest here. The world is wide and strange, and full of things we have not yet understood. And that is a wonderful thing to fall asleep beside. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.